Myself, Manu Mehta, faculty with Photogrammetry and Remote Sensing Department, Indian Institute of Remote Sensing. And I'm here to present a discussion on image pre-processing, especially for optical remote sensing images. So I assume that the audience which is present here should have a knowledge of a background knowledge of remote sensing, what, why, and how part of it, and different regions of electromagnetic spectrum where remote sensing is carried out for Earth observation. So with this, let us begin with today's session. So for optical remote sensing, I'm basically referring to those spectral regions which are covered from 0.4 micrometers to around 3 micrometers. This covers the visible portion of electromagnetic spectrum along with reflective portion of infrared radiation. Infrared radiation has a large span of wavelength range starting from around 0.7 micrometers to around 100 micrometers. However, only the portion of 0.7 to 3 micrometers is considered for reflective type of remote sensing, whereas for 3 micrometers up to 100 micrometers, those regions are more suited to thermal remote sensing. So whatever pre-processing techniques I'll be discussing with you today will be majorly referring to the visible plus reflective portion of infrared, that is 0.4 to 3 micrometers. All right. So with this, there is a need of image pre-processing of remote sensing images. Sometimes we call it as restoration of images, and when we talk about geometric corrections, then we require rectification process also. So we'll discuss each one of these one by one in the due course of the session today. And we require to correct for sensor and platform specific distortions of the data. Now there can be two types of distortions in any kind of remote sensing data. One could be radiometric and the other could be geometric. Radiometric, as the name suggests, if there is a change in the digital number value of any remote sensing image from its actual value, that is a radiometric error. So for example, at certain pixel, if there had to be 10 units to be recorded at the sensor, instead of 10 you record 11 or you record 8, that is a radiometric error in the data. So where we talk about the changes in the values. However, if you talk about the changes in the position of the digital number, we refer this to be geometric errors. That is, the position of DM or the position of the data changes from its actual position on the space of Earth, then we call it as a geometric error. So both the types of errors can be present in the data, both radiometric and geometric errors. And both these types of errors can be systematic, that means you can predict it. So we call them as internal errors. The others could be non-systematic or non-predictable. We call them as external error. So if you have a systematic error, you can easily model it because you know what the error is. So you can model it, find the model and then correct the error. However, if the errors are non-systematic, can't predict them, so you need to have an approximate assumptions to the model and then you approximate the reality. So it's easier always to correct for the internal errors compared to the external errors. Both true for the case of radiometric and geometric errors in the remote sensing data. Now, as I said, radiometric corrections need to be done for correcting the digital number values, which the errors can arise through several reasons. I'll discuss them one by one now. And there could be errors in the geometric position of the pixels. So we convert and correct the data to fit to the true position on the Earth surface. This can be applied to extraterrestrial data as well. Now, coming to radiometric errors, in a major way, there are two types of errors. We can classify them as systematic errors or system errors and the others is atmospheric errors. The system arising errors could be due to mechanical failure or electrical failure, or there can be some failure while the data is communicated from onboard to the ground. So accordingly, we have several different types of errors. We can have dropouts, we can have striping or banding, we can have line start errors. All these types of errors can be only minimized by cosmetic corrections. That means because the data was not recorded either, or it was recorded but was not communicated properly, so that the data lost is lost forever. However, because the Earth's features are very much correlated to each other, they don't change abruptly from one pixel to another pixel. So taking this information and using this reality, we can cosmetically do some corrections. Artificially, we can correct the data, but we can't retrieve the data, right? So we call them also as cosmetic corrections. I'll show you some examples. But before that, just have a look at these stripes. Now, these stripes can be in either directions for a raw data, which is stored in the terms of rows and columns. You can have totally dropped lines, or you can have striping, like these values are all very high at certain intervals, okay? Or you can have combination of these. You can see the bandings. You can see dark lines and the bright lines also. Now, how these errors are caused? See, we have two types of scanning mechanisms. One of the major scanning mechanism is based on push-broom scanning. What we do here is, we have a linear set of detector arrays. We call them as CCDs, charged coupled devices. Then we have an optics to focus, right? The data is coming from this line on the ground. So for each pixel, you have a CCD. This pixel is mapped to this CCD. Then accordingly, you will have as many CCDs as there are pixels, or there are different sets of data elements in a particular swath line. Now, if suppose one of this sensor goes bad, this scanning is done in this manner. If suppose this sensor, this corresponding CCD has gone bad, the last CCD I'm talking about, so you'll have a dropped line continuously in this column, right? So if you have a data arranged in the terms of rows and columns, and if you have these set of pixels stored in different columns, you will see that you will have a dropped column here. The other instance could be that the detector says the detector saturation limit has reached. So in that case, you will observe white lines, the stripings. Okay, this you will see when you have a push-broom sensor. So one complete column will be dropped, or there will be striping. So you'll have bad columns in the data. Another type of scanning mechanism is a cross-track scanning, where what we have is, we have a mirror, a large telescope mirror, and then we have a rotating scan mechanism. So there is a motor attached to it, and the mirror keeps on scanning different lines. So suppose now this data is gone to a set of filters, and suppose one of the filters is gone bad, so you'll have striping here in the across direction, this way. So the same case is shown here. This is called Landsat. So you can see dropped lines, and then you have a regular kind of striping here, which will occur. This is a bigger portion of the picture, which is taken, a part of it is shown here. So you can see a complete set of banding is observed in the data, right? This is for a cross-track scanner. For in a long-track scanner, you will have dropped columns. Instead of the horizontal lines, you will have vertical dropped lines or stripes. Bad columns, we call them, right? So what do we do Now we assume that the Earth features are very well correlated with each other. So even if you have one line or one column or one row dropped, what you can do is you can take the pixel values of that dropped line above and below. Take the average and replace that column or line with the average of the values. So here we assume that there is spatial correlation, and this you can do for different bands. Similarly, the same technique can be done for striping errors, but there are certain other types of methods. You can use some calibration data. You can use histogram matching methods, and that can be parametric or non-parametric. Other type of errors, that is line start. So you can see that in certain data sets, you might have observed that in the beginning of a line or a column, the line is dropped. So in that case, you can do horizontal adjustment or line by line basis adjustment, similar based on drop line correction method. But all these types of methods of correction are not corrections actually. These are just cosmetic corrections. So any of the code you can write for correction of the data, but mind it that you should use such kind of correction methods before doing the geometric corrections, because then you'll have the data in either rows or columns, dropped ones or striped ones. These will be either horizontal or vertical. So you can easily replace the data which is missing by the data in the adjacent rows or columns. Right. Now coming to atmospheric distortions, this one is more complex, because here the electromagnetic radiations are also interacting with the atmosphere along with the interaction with the target. So whenever there is an interaction of electromagnetic radiation with the atmosphere, you have either scattering and or absorption. So scattering means, suppose the light is coming and it hit a particle, part of it can be scattered to different directions. So redirection of light. And absorption, the light which was coming and then it hit the particle, part of it can be absorbed by the particle. So such type of distortions do take place and will be specific to different locations, different times of the year, different seasons, and different times of the day also. Another kind of distortions could be topographic attenuation. So depending on the elevation levels or slope and aspect of the places, you may have distortions due to topography of the data. So for this, you have atmospheric correction methods. So for atmospheric correction, again, we can have relative radiometric corrections or absolute radiometric corrections. So for relative radiometric corrections, we can assume the haze effect or the effect of the atmosphere to be additive or multiplicative and use different models to fit in to correct the atmospheric errors. These are simpler and are found in several image processing softwares. You can yourself write a very simple algorithm to do it. But for absolute radiometric corrections, you need to model the atmosphere. That means at the time of acquisition of the data, what was the condition of atmosphere? What was the condition of gases present in the atmosphere? What was the local pollution there? Have you done any field measurements of the atmospheric conditions or not? And then you have pre-written radiative transfer models. Some of them are licensed versions and some of them are freely available to use. Success is one such freely available code. Atcar, Martran, Dassault, Atram, these are all licensed versions generally. You can yourself also model the radiative transfer and correct for the atmospheric conditions. But for that, you need to either go for physics-based modeling, or you need to have large set of lookup tables to which can let you estimate the atmospheric conditions at the time of image capturing. So both the types of correction methods one can opt for. One can opt for relative corrections also, which are good enough if you are going for qualitative remote sensing approaches. For example, if you have project on change detection. Okay, how much part of the forest is, has been removed, or what are the changes in the urban features, etc. So, people images, you can very well go for relative radiometric correction methods. However, if you want to estimate some parameter, just quantitative, let's say soil moisture, or some quantitative parameters of the trees or the crops, then you need to go for absolute radiometric corrections. Okay, so in the coming classes, I'll be discussing more on relative radiometric corrections separately and absolute radiometric corrections as well. So now coming to geometric errors. There, again, as I said, there could be systematic distortions. These systematic distortions could be due to the motion of the sensor and the platform. And also because the platform is moving from, let's say, north to south or from south to north for the polar satellites with respect to the Earth. So, and the Earth is also not stationary, it's also moving. So, there can be geometric distortion arising due to the rotation of the Earth. I'm going to discuss each one of them one by one. And then there could be non-systematic distortions also, or random errors, which are more commonly found for aircraft platforms. Because several times during aircraft remote sensing or air-based remote sensing, you need to alter the altitude and the attitude also of the platform. So these as kind of errors become non-systematic or random errors. And we'll see each one of them one by one. Yeah, but before that, I'm going to discuss. Yeah, give me a minute. I'll just show the kind of geometric errors which are commonly found in the remote sensing images before I go to geometric correction of the same. 2 minutes break here, and I'll be just back with the kind of geometric errors which are commonly found in remote sensing images. Let me just get the PPT and then I'll be back to you. As I was discussing about various types of geometric errors, let me show you some of the errors here. What kind of errors can come up? So because there is a forward motion of the platform, right? And during the time of each mirror sweep, if I'm talking about the cross-track scanning. So in the cross-track scanning, you know that the mirror is moving continuously from one side to another side across the direction of the motion of the satellite. So by the time the mirror reaches back to the same place, there is a forward motion. So what happens is that the ground swath is not normal to the ground track, so becomes slightly skewed. So instead of having this clicks along this line, this dotted line, you have a shift in the images captured by the satellite, because the Earth is, by the time it has little bit rotated, so you will have a skew of around 1 pixel at this edge to this edge. So this is a cross section of, or cross scan geometric distortion. We call it as scan skew. This happens only for across track scanning platforms. Then another could be mirror scan velocity. Now, usually when there is a scanning of across the track, the scanning rate is usually not constant. So you generally have a long scan geometric distortion when you have a non-constant scanning rate of the mirror. So actually, with time, the mirror angle should be changing in this linear fashion. However, the actual takes place like this. So you will have along the scan geometric distortion. The previous one was a cross scan. This one is a long scan, both happening for a cross track scanning platforms. Then another kind of geometric distortion could be panoramic distortions. Now, what happens is at the nadir, and if you see at the corners of the swath, the effective pixel size on the ground is larger at the extremities of the scan line than at the nadir. Because this is how, if you can see this, because at this end of the swath, at these extreme points, more area is captured by the satellite or the pixels compared to that done at the nadir. So this type of image you will have. So at the end you can see that actually this at the end you cover a larger portion, because you are looking at the extreme portions of the data. So this type of distortion will occur when you have a large swath capturing cameras. This does not usually happen when you have a smaller swath of the satellite sensor. Then suppose there is a change in the speed of the platform. So what happens is the ground track covered by the successive mirror scans will be changed. Okay, so you will have, suppose the velocity has increased suddenly, so we'll have greater image, a greater area now. So this kind of error of change in platform speed will also cause a long track scale distortions. This happens more commonly in aircraft-based remote sensing methods. Then one of the most commonly occurring error in any kind of remote sensing images is due to the Earth's rotation. Now we all know that Earth keeps rotating from west to east, and movement of the satellite is either in north to south or south to north. Now I have considered it from north to south here. So what happens is, actually it should have, if the Earth would have been stationary, this black rectangle would have been the picture captured by the satellite. However, the Earth keeps on rotating from west to east. So this arrow is showing from west to east. This arrow is showing from north to south. So subsequently, the area which is seen by the satellite is shifted from this rectangular to this parallelogram. So this type of error occurs. So I have just discussed the kind of geometric error which commonly occurs due to the rotation of the Earth while the satellite is capturing the data, right? So I have shown you an example when the satellite is moving from north to south while the Earth is moving from west to east. So you'll have a skewed kind of data which is collected, but it is stored in the form of a rectangular shaped data only, the subsequent rows and columns only. However, the actual coordinates on the ground, the data has been captured in a skewed manner. So what we do is, we take a reference image and we take the image that we need to correct. Now, if the reference image which I'm using, if it is a topo sheet, or if it is a ground-based collected information from GPS, then the process is called rectification. That is, you give the actual coordinates of the ground to the image that you need to correct. So your master image becomes the topo sheet and your slave image becomes the raw data. So using this information of latitude and longitude on the base image, you give the planimetric geometry of the image to be corrected. That is your raw data. So whenever we require accurate measurements of direction or area or distances, we need to go for rectification. However, suppose there is a condition, there is a situation that you don't have actual topo sheet of the data, or you do not have the actual ground coordinates of the data, but still you want to make some comparative analysis. What you can do is, several times we have the geometrically corrected images of certain areas, and we have another image which is raw data. So using the reference image as another image which is already registered or rectified, you can use that image as the reference image, and you can correct your base image with respect to that. Now the problem here is, whatever be the errors, whatever be the geometric errors in the reference image will be inherited to the base image also. However, if you are doing some change detection kind of analysis or multi-temporal images, or you just want to see how temporally some features are changing, that time this kind of image restoration works very well. So you need to this process is called image to image registration. So, for example, you have a reference image as a Landsat data of maybe which is acquired at some another time, but you have a current data from some other sensor, from sensor A or B, and from this Landsat image, you can get the information of latitude and longitude, and you can register your own image with respect to that. So whatever be the errors in the Landsat data, which is geometrically corrected or rectified, those all errors will be inherited in your sensor 8 data, which you are going to correct with, right? So sometimes we use hybrid approach also. For example, you need to go for, let's say, some time series analysis. That time, sometimes we first rectify both the images with respect to topo sheet. And when at the time of comparison of the two images, because rectification also, you will use some model, okay, some approximate model to map the image to the actual topo sheet. However, this model will have certain uncertainties. So at all the points, it might not be possible for you to give the actual planimetry geometry of the image. So at that time, what you can do is first you rectify the image with respect to the map that you have. Then when you want to do some change analysis, then you geometrically co-register one image with respect to other also. This is very commonly used method in the remote sensing, that we do rectification also, and we do then image co-registration also. Okay, so for any geometric correction, we need to have some reference points from the reference image. These points are called ground control points. These can be obtained from topo sheets for rectification, or from GPS, or for registration, you can obtain it from any other satellite image also. So we have two steps of geometric correction. One is spatial interpolation, and the other is intensity interpolation. So what we do is, I'll show you with the help of this example. You see this, the yellow and blue marked image, right? So this is your raw image. You have to map it to the actual geometric configuration, which is shown in the yellow empty pixeled image, this grid. So this filled color image is your raw data. This empty colored pixels in the grid is your reference data. So there are two steps before you. First is you set up a mathematical relationship between the initial grid and the final grid. Initial means your raw data and the actual reference image. So first is the creation of a mathematical relationship between these two grids. And second is, when you have created this reference grid, you have to map the actual DN values to these pixels. So how would you do that? This is called intensity interpolation, or we call it as resampling. So as I said, in spatial interpolation, we establish a relationship between the input pixel location and the associated map coordinates of the same point, that is your GCPs, right? So this is using ground control points. We choose some points which are visible clearly on the raw data as well as on the reference image. These could be some crossings, let's say some two road crossings, or the crossing of a road and a canal, or the corners of some buildings if the data is at a very high resolution, or it can be the corners of some villages in between, or orchards, or wherever you'll have corners or such points which are not going to change much with time. You can choose all those points as your GCPs. Now, you should not choose points if they are likely to change over time. For example, the edges of the forest, don't choose it. Or the course of some rivers, no, don't choose any point, any such point which is easily visible also, but is not going to be constant over time. Okay, because it is not necessary that the reference image and the image that you need to correct are taken over the same period of time, right? So we choose some GCPs and then we fit some polynomial equations using least square techniques. Okay, so minimize the error in the polynomial equation, fitting the GCPs from one grid to the other. Okay, so it is like a mathematical linkage. So we have addresses of 1 pixel in the you have chosen some GCPs. These GCPs have some address in the raw data, and these same GCPs have another address on the reference image. So you have to map a mathematical linkage between these two addresses, right? So this once done, now how to fill the grid, the output grid which you have created, you need to fill it with the DN values. So because what happens is in the image which you have created, this pixel grid you have created, you can see that this one pixel is not fitting properly well into the corresponding pixel on the other grid. So for example, if you look at this highlighted grid, a highlighted pixel in the output grid, you can see portion of B, portion of A, portion of this B and this B. All are covering some portions in this pixel. So how do you fill this pixel? One of the easiest way is you dump in that value of the pixel which is having the most of the area covered over this pixel. For example, here A is contributing most to this pixel, so you fill in the value here in the output grid in this pixel as A. So this kind of mapping is called nearest neighbor mapping or nearest neighbor resampling. So what happens is the pixel in the new grid gets the value of the closest pixel from the old grid. So you will retain the original digital number values. Okay. The other method is, because this is not the actual good method here. Why? Because some portion of this pixel was covered by the neighboring pixels also. So what you can do is we can take the information from the neighbors also. How you would do it is, one way is you can take the average of all the 4 pixels which are falling over the new pixel, right? So here you will have contribution from all the neighboring pixels also, and the actual pixel which was having the maximum portion covered in the output pixel. So you will get a smoother picture. You will not retain the actual DN value because now it will become A plus 3 times B by 4. So this actual DN value is gone. A new DN value is created, but your output will be more smoother. Now, another way could be, for more smoothness, you can take the information of other neighbors also. So instead of having 2 cross 2, you can have 4 cross 4. This 4 cross 4. All these 16 pixels are averaged, and then you can get the value substituted in this pixel. Now here one important point is, while doing the average, we do not do the actual average, we do the weighted average. So here, how much percentage of A is coming, that particular weight is given to the value. Okay, so you, instead of doing simple average, you do a weighted average. So the value is more close to the actual DN values. So more the amount of such kind of neighboring information you keep on adding, more smoother will be the image. So you have a nearest neighbor or bilinear or cubic convolution approaches usually built in for all the pre-processing image-based softwares. However, you can write down a model of your own also. All right. So this is one of the major geometric correction methods which we utilize for our rotation. For example, this is the image which is created using nearest neighbor method. However, the same with shown with cubic convolution. So this has got more smoother. Now, this is one question which I'll put for you, all of you to answer it to me, why such kind of skewed stripings are observed. So in the interaction session, when I'm taking up the questions, I would also request you to answer me why such kind of skewed banding patterns are observed. Now, in today's session, I have discussed with you the major types of radiometric and geometric errors. And just an overview, I've just touched upon the radiometric correction methods, right? I have not gone into the details of that. The next two sessions in this webinar are focused majorly on the radiometric corrections for relative mode as well as for absolute mode. One by one, we'll be discussing in the subsequent sessions. And I've covered somewhat in depth the geometric correction methods which we can use for your remotely sensed images. Because anyways, for all the RS images, you will need to do geometric corrections if these are in the raw data form. So with this, the session from my side is over. I'll be waiting for some questions from your side and will be happy to answer them to the best of my knowledge. Let me give you 5 to 7 minutes break and then I'll be back